Hello 5480 students. Today we're working on the review packet for Unit 8. That's the magnetism unit. Remember, I want you to do the whole review packet first. Then check the answer key that's posted on Drive. And finally, watch this video. At the end of this video and before your test, you should be able to do everything on this objectives list. So let's go through it. The way this review guide works is everything in this first section is on the first page of the review. So let's go check that out. First page of the review, permanent magnet. So where's the North Pole of this magnet located? In this picture, we have domains, and the domains point from south to north. Domains point north and are on the inside of the magnet. Field lines point south and are on the outside of the magnet, forming a nice closed loop. Look how if you followed this line, it would make a circle. Field lines and domains connect. So if D is the North Pole because the domains point north on the inside of the magnet, then D is the North Pole, and A is the south. The permanent magnet in the picture can be made of anything except for copper. Copper is a non-magnetic material. Basically, its electrons don't line up correctly. One always points up when the other points down. They cancel each other, so copper can't be magnetic. Only iron, nickel, and cobalt can be magnetic materials naturally. If iron is a magnetic material, it can't pick up paper clips, right? An iron skillet can't pick up paper clips in the same way that like the iron in this clipboard can't go pick up paper clips. It's iron, it is a magnetic material, but the domains are not aligned, so it's not yet a permanent or ferromagnet. The paper clip is not a magnet because the skillet's domains are not a magnet because they're not yet aligned. So it is a magnetic material. The answer is not I. The paper clip is not a magnet, but that doesn't explain it. And it definitely can't pick up paper clips. Now, not that I have students that would throw things they're not supposed to. 1D. While playing darts with some bar magnets, one of the magnets breaks in half. Well, they each remain magnetic. So imagine this is your bar magnet, and it breaks in half. Well, originally the domains pointed from south to north. They point north inside a magnet. But when it breaks apart, the domains don't shake out of alignment, which means this is still a south pole, and this is still a north pole. So when it breaks in half, it makes two separate magnets, so they are still just as strong as the original unbroken magnet. Next, draw the magnetic field lines for the following magnets. Oh, and this is a brand new cutting board. My husband actually just made this earlier this week, so the oil from it is seeping through. Sorry about that. Right. So magnetic field lines point from north to south, and they are on the outside of the magnet. From north, so away from north poles, towards south poles. A thing you should be able to do with this then is identify unknown poles. Let's say I had a magnet facing this way, or a compass facing this way. Compasses point towards south poles. Compasses point south. Since where the Arctic Ocean is technically a magnetic south pole, the compass points there. Finally, if you know where the field lines are, you can figure out where north and south are. If a compass is pointing away from this pole, this must be a north. And since magnets are dipoles, this must be a south. Remember, a dipole means that the north can't exist without a south. They must have both together. It's kind of like heads and tails of a coin. You always have to have both. So this shows attraction. This must be a north pole, and that must be a south. And to confirm, the field lines are pointing at the south pole. Field lines and compasses point towards south on the outside of a magnet. Domains are on the inside of the magnet and they point north. So everything on the first page should get covered by this. So we talked about how magnetic poles create permanent magnets when they are aligned. Check. We know they're dipoles. They always have a north and south pole. We're going to get to this describe force interactions on the next page, so I'll get to it. The magnetic field around a permanent magnet points from north to south. So we talked about that. Be able to draw it. That's the whole thing where when it points away from north and towards south, you're drawing lines that are this shape that take up the whole space. The lines cannot cross each other. They should take up the majority of the space they're in. So you get points for shape, direction, taking up the whole space, and the lines not crossing. 4 points. And we talked about using a compass to determine the poles of the magnetic field. Number 2, solenoids. The right-hand rule for solenoids involves determining the direction of current first. And in this case, it's drawn for you already, but in case you have to do it yourself, this is conventional current. So it's going away from a positive charge and towards a negative charge. So this must be a battery with a negative over here, then positive and up. Now, curl your fingers in the direction of this conventional current, just like it's drawn here. So your fingers are curling up. When I curl my fingers on my right hand in this direction, it forces my thumb to point to the left. That must mean that D is a north pole. And because magnets are always dipoles, that means B is a south pole. The south pole of the device is located at B using the right-hand rule. This is an electromagnet because its magnetic field comes from the current going through this wire. Now, let's practice this right-hand rule again. I'm pointing my fingers in the direction of current, curling my hand. Oh gosh, that's uncomfortable. Curling my right hand. So my fingers are going in the direction of field. My thumb points north, so this must be a south. Okay. On the other end, curling my fingers in the direction of this field. My thumb points to the left, so that must be a north. If you're a steps person, I'll write the steps out on the key for you. You want to curl your fingers in the directions of current. So curl current, and your thumb points north. From there, here's the force interaction between two magnetic poles. If this is a south and that is a south, these repel each other because like poles repel. A student has an electromagnet that creates a field B. Determine how the magnetic field changes if you quadruple the number of turns and cut the current in half. The relevant equation for this, you don't have to go math out, you just need to be able to do proportions. This equation says the magnetic field of my electromagnet depends on permeability, that's the core, the number of coils, the current, and the compression, how close together those coils are. If each coil is its own little mini magnet, then when you put them closer together, their fields add up constructively. So let's see, if I quadruple the number of turns, if I make N 4 times as big and cut the current in half, well, increasing the number of turns made the field stronger, but decreasing the current made the field weaker. This new field must be twice as big as the previous field. Now some students come along and they're talking about the permeability. And a student claims replacing the iron core with nickel will be more effective. But that's not true. Iron has a higher permeability. It has domains, and those domains are easily aligned. Iron has a higher permeability, and that makes it a better magnet. It has a stronger magnetic field. So as permeability increases, field increases. Think of it like this. Whenever the current is on, right, it's running through this coil. When the current is on, it causes the domains to jump into alignment. Whenever the current is off, then all bets are off. The domains just go back to whatever they were doing before. So if it doesn't have domains, it can't have a field. That's why copper can't be used here either. So a student says copper can be used because like they're both metals, right? But copper is not magnetic. Copper's permeability is functionally like 1 or something like that, whereas iron's is 6,000. Copper doesn't have domains, so its permeability is small, making its field weak. Just to double check here, we've done the electromagnets, so you should be able to talk about the direct relationship between core, coils, and current. Increase any of those three things and you make the solenoid stronger. You need a ferromagnetic core because you need the ferromagnet's domains. If you can make those domains do your bidding, then you make an adjustable, strong magnet. Finally, we know where the North and South Pole are because we use this right-hand rule business. Good, so let's do fields from straight current carrying wires. For this, you should be able to identify that the fields always make circles as the current travels. Remember that electricity always creates magnetism. So you're moving electrons going through this wire here, creating the current measured by the ammeter. The current makes the magnetic field. And the conventional current in the wire, it says what direction is the conventional current traveling? Well, it travels from positive to negative, and hey, the current has an arrow on it. What direction is that arrow pointing? Down. What about the magnetic field? You can see the magnetic field in this because in the background, do you see that compass? Like I know it's making a circle here. It's got this compass, and the compass is pointing in this direction. What direction is that? That is clockwise. Now, to be fair, you can totally cross two choices off of both A and B because my current is traveling in a straight line. This is a straight current carrying wire. So the current is not going in a circle because the wire is straight. And I know the magnetic field for a wire always forms a circle, so this can't be into the page or down. You see? Now you get it down to two choices and you can just 50% guess. If the battery were reversed, the compasses should switch direction. So right now they're going clockwise, but if you switch the current, they should go counterclockwise. Ta-da! Okay, so let's say my field is 6, and everything above the wire has field that's going out of the page towards you. Okay? And if the current in the wire is reversed, it'll still have the same size field, but in the opposite direction. So in this, I'm going to say the field is still going to be 6 Tesla, but reversing the direction would be reversing the direction of field in opposite direction. So imagine that at this point, P has a field that's pointing out of the page at you. It's forming a circle, it's doing this, right? Kind of hard to draw because it's not on the page. It's not in the X and Y direction. So as the field is coming out of the page, if it goes back to the other side, that'll be going into the page. All right, but what if I make a point that's twice as far away? And it says draw the point. I can draw that. It's right here. We got that. If it's twice as far away, my equation for field says that it should have half of the field, right? If I double R, I get half of the field because this is an inverse relationship. Now, if you're a proportions person and you're saying, but what about the 2 pi, Mrs. Besega? You can actually ignore them because those are universal constants and proportions only care about the change. You can ignore the 2, the pi, the mu, right? The magnetic field is half as strong because it's twice as far. And you could imagine it on this picture as well, if it helps. Your field here would be strong, hence this nice, like, close together field lines. Field at P would be strong. Field at Q, which is twice as far away, would be weaker. Finally, how do I make the current, or how do I make the field stronger? If I want to make the field stronger, I could change the current. This equation says that if I change the current, that has a direct relationship on the field. So tripling the current should triple the field. And it will still be in the same direction, right? Because like making this current stronger would just make the field at P stronger. Nice. So notice with these equations, proportions here, not lots of crunching math numbers. Doubling the radius makes it half the field because it's an inverse relationship. Tripling the current makes it triple the field because imagine I put a 3 right here. That's a direct relationship. And to double check, describe that the magnetic field is a circle. Draw the magnetic field. Draw a circle. Describe that magnetic field has a direct relationship between current and an inverse relationship with distance. If it helps for you here to come up with 2 graphs, if current goes up, then field goes up. If radius goes up, then field decreases. Yes. All right, so now let's talk about planetary magnetism. I love earth science. I think it's so cool. Let's say that this is the mid-oceanic ridge. The ridge is right in the center here, and magma is pushing up between the 2 plates of the earth. Right? As it pushes up, A is the youngest and E is the oldest, because like A is literally touching this brand new baby rock. E is like a fossilized grandpa. The old rock has been pushing out away from the center of the seafloor for millennia, literal millions of years. So E was around when like dinosaurs were around, and A is like coming out of the ground right now. Now the strips alternate in direction of magnetic field because remember, the magnetic field of the Earth is not a constant. Sometimes the magnetic field of the Earth is over here. And as these rocks cool, the iron in them solidifies. And it solidifies with its domains pointing towards where north was at the time of alignment, at the time that it cooled, right? So sometimes north was over here. These are parallel to each other because this plate used to be over here, so north was still that way. But other times, the poles move. Consider this like a fossil record. It tells you when in Earth's history did the poles move? How fast did they move? How frequently did they change? So the strips alternate in direction because the magnetic poles of the Earth move. They change. The magnetic poles of the Earth move because, I'm going to skip a question right here, because of the liquid inner core. So you know you've got the nice crusty crust, solid, crunchy lithosphere out here where the, tectonic plates are. Those get moved by the mantle, which is squishy rock, like the consistency of a Snickers bar. Yum! Under the mantle, which is the squishy rock, there's the inner core, and that's where the fun happens. The inner core causes the magnetic field because it's made of molten iron. Or sorry, the outer core. Gosh. It's made of liquid iron, and as that iron spins, it carries its electrons with it, creating a dynamo. Well, that dynamo creates the field of the Earth. As those currents churn and burn, the south pole of the Earth is up here by the Arctic. The north pole of the Earth is down there in Antarctica with the penguins. That creates the magnetic field of the Earth that points away from north and towards south. That's why compasses point towards the Arctic, because that's a south pole, right? Right. So the liquid layer causes the Earth's magnetic field. Because that liquid layer can move about randomly, that's why you get the flipping, as evidenced by the ocean ridge seafloor pattern. So that proves tectonic plates move. Other evidence includes plant fossils. Remember from when we put together the Earth? Animal fossils. The Earth's overall magnetic field changing. The mountain ridges, right? The magnetic strips. The only two pieces that don't contribute to this picture, because we didn't talk about these at all, right? Hominid fossils. Guys, our ancestors did not exist in hominid form back then. We're talking about millions of years ago. At that time period, our ancestors were like little tiny ground mammals, like rat-sized. We were probably pretty furry and cute. And we certainly didn't have human language. Some estimates on human language are around 50 million years ago. But written language that we can, understand and translate is only about 15,000 years. So not human language, that's not enough time, and not hominid fossils. Finally, why is the Earth's magnetosphere, this blue that I drew out here, important to protect life on Earth? Well, let me tell you about the angry sun particles. One of my students in another class called solar wind, the angry sun particles. So let's draw an angry sun over here. It's got sunglasses, but it's not super happy about us. And yes, the sun lets off light, but the magnetosphere can't protect us from that. All the light from the sun's gonna hit the Earth. Cool. But the particles, those fast-moving electrons, the fast-moving hydrogen atoms, these ions that we want to avoid, when they interact with the magnetic field of the Earth, they spin. You might remember from my Aurora demo that it created a circle. Well, as these interact, some just go straight around the Earth, creating kind of a slipstream effect, but others will follow along the field lines and collect at the poles. At the poles, they hit the oxygen in the atmosphere. They they excite the oxygen ions, or oxygen atoms, and release light. This both creates the auroras, which appreciated, but also prevents those particles from hitting us. Remember, here's where we are. If the particles hit us, it can kill the cells or cause mutations, right? If the particles hit something like a bacteria or a single-celled organism, it can kill the organism outright. So, thankfully, the Earth's magnetosphere, this magnetic field, protects the Earth from charged particles. I did notice that on here it has some few extra things. We did not get a chance this year to talk about abduction and subduction zones. It's basically like where sometimes the plates come together to create mountain ridges, and sometimes the plates move apart, like the mid-oceanic ridge. But we didn't really talk about those. You should be able to talk about Pangea, the mid-oceanic ridge in the Age of Rocks. Describe Earth's magnetic field as having a north pole in Antarctica and a south pole in the Arctic Ocean. The cause of the magnetic field, which is that liquid churning and burning layer on the liquid outer core. And finally, the importance to the magnetic field to life on Earth. It protects us from solar wind particles. All right, on to section 5, magnetic force on a current carrying wire. This equation is force is equal to ILB. The field creates a force on moving charges. So if there's twice as fast charges, so if I doubles, I should have twice as much force. That's what a direct relationship means. So I need to cross out these two choices. I know it should be more force. And switching the direction of current switches the direction of force. One way you can think about this is there are 3 vectors here. And if you switch either I or B, then a force has to switch with you. So you switch the direction of field, you must switch the direction of force. If you switch both field and current, well, then you have a force that's in the same direction. It's like having a double negative. All right, so now, show the direction of conventional current. Guys, this is the 3rd time I've asked about conventional current. I think it might be important. I don't know, man. But I know that it goes from positive to negative. So it must be going up through this wire. Current is going up. These little X's denote a magnetic field that's traveling into the page away from you. So picture it like pointing away from you, right? And it says the magnetic force pushes the rod to the left. Let's push that to the left. So there's my force. Label the force F. Done. Calculate the magnitude of force. This is the only math question I've asked so far. Force is ILB. So I is 2 amps. L is 0.4 meters. B is 0.5 Tesla. All in all, that makes 0.4 newtons. And since it's magnitude, I don't need to include the direction. I know it points left anyways. And since it points left, this railgun fires the projectile at the power supply. If I'm talking Navy level projectiles, I don't want that facing my ship. So I could change either reverse the current, right? Reverse the current or reverse the field, and you reverse the direction of force. So reverse either field or force. Well, how do I make it faster? Well, that equation says I can increase I, the current, L, the length of the rod, or B, the field. If you want to be more thorough, how do you increase the current? I could increase the current by increasing the voltage or decreasing the resistance, because then it would prevent fewer electrons from running through. With an increase of electrons, you have more current. So I could increase the number of batteries. I could increase the power supply's voltage. I could decrease the resistance of something in the system. And I can also decrease the mass, because decreasing mass increases acceleration by Newton's second law. As far as energy transformations, notice this starts with a battery, so that's my electrical energy. Electrical energy is the input of this system, and it causes this projectile to move. So kinetic energy must be the output of this system. An item that causes motion is a motor. A motor causes motion. So in this case, electricity turns to kinetic energy. This is a motor. because it creates motion. All right, electromagnetic induction. In this case, a magnet is moved through a solenoid, creating a current in the coil. This voltmeter reads voltage. The electrical energy comes from the kinetic energy that you put into it. Think like you're the person that's moving the magnet. There you are. You're the person that's moving the magnet, so your kinetic energy moves the magnet, pushes the electrons, creates the electricity. Now, it says if it's pulled quickly to the left, you get a current. So let's draw that velocity in there. If you moved it to the right, you've reversed the direction. So I'm looking for an answer that says opposite direction. And you move it more slowly. You put in less kinetic energy, so you should expect less current. The answer to that one is I. Next, the North Pole slowly moves towards the coil and makes a small positive current. What happens in each of the following cases? And notice you need to circle two things. What happens to the size of the current? What happens to the direction of the current? So you started with the North Pole, and north going towards the coil gave you a positive. If it's still north moving towards the coil, you should have the same direction. But the faster speed should give you more current. As speed increases, you put in more kinetic energy, so more electricity. If you move it away, you've switched the direction, so the opposite direction. Slower rate, less kinetic energy, less current. What if you slow it all the way down to 0? You get no current then. A south pole moving towards the coil at the same speed would have all the same properties except opposite direction because south instead of north. So I would expect the same current but switching direction. This last one is a little tricky. The south pole moves away from the coil, so you've switched the direction of velocity. And you've switched the polarity. You switched two things. That is a double negative, so I would still expect a positive voltage. I would expect more current because you have a faster speed. So what do I want to do to make the most voltage possible? And don't you say add more batteries. There are no batteries here, guys. No batteries. You move the magnet, it induces a voltage. If I want it to be the largest possible voltage, I need to put in more coils. I need a stronger magnet. I need a larger coil. L, I want you to think larger coil. And V is speed or velocity. Move it faster. So I don't want to see anything about resistance or batteries in this question, because in this scenario, what's being changed is the movement of this magnet. How can you move this to make more voltage, right? So let's double check our last bit. Notice this was not mathematical, just proportions. So whenever you have a changing, moving magnet, you get a voltage. If the loop is closed, and it was in problem 6, then you get a current. You can have more voltage by changing the strength, speed, length, and N, the number of coils. So if you have more coils, you get more of these. For the direction rule, you have two vectors here. The velocity that you push the coil at in the field. If you switch one of those, you switch the direction of voltage and therefore switch the direction of current. If you switch both of those, it's double negative because you flip it once, flip it twice, and you're back. Motors and generators got built in as we go. A motor causes motion, so it turns electricity to kinetic energy. And a generator creates electricity. A generator generates electricity. So it puts in kinetic energy, like you move the magnet, and it makes a voltage, therefore electricity, from that. All right, everyone, best of luck. If you need help with that right-hand rule, this is the only right-hand rule you need to think about. Good luck on your test on Monday. See you soon.